Hello guys and gals. This is going to be our last video on 5.3 because all I'm going to do in this video is finish up the practice problem we were working on in the last video, and then that's it for this section. There's another practice problem you can do on your own, and you can come and ask me questions otherwise, okay? So we had just finished with part B on this first practice problem here. Let's look at part C, okay? Determine the concentration of N2O5 at 600 seconds. Does your calculated answer make any sense, and justify that answer? Well, again, they're asking for concentration, but they've given us a specific time. So because they've mentioned time, we have to use the integrated rate law. And because it's first order, we're going to keep using this exact same formula. We will not use any other formula. We can't, because this is the first order formula when it's integrated rate law, okay? I'm going to solve it a similar way I did before. I'm just going to substitute the answers that I already know. I solved for K, so I have my negative K value here. I already know the natural log of my concentration initially, which is here. And then here they've given me that I'm doing this at 600 seconds. So I'm going to go through, make sure that you solve for the concentration and not the natural log of the concentration, right? If they wanted the natural log of the concentration, you could stop here at this third step. But they don't want the natural log of the concentration. They don't want the point that's on the graph. They want the original concentration. So we have to raise everything to the E, and that will give us 0.00157 molar algebraically, okay? So does this answer make sense? So 600 seconds is 200 seconds past our last data point. So whatever our last data point is, this concentration should be much smaller than our last data point, because our last data point's at 400 seconds, and the concentration there is 0.00625. Well, because we're looking at the rate of disappearance of our reactants, our concentration should be much smaller at 600 seconds. And that's true. 0.001 is much smaller than 0.006, and so this answer does make sense. Now, you will not have to answer questions like that on the AP exam, but it's important that we go through them here to make sure that you do that to yourself on the AP exam. If you get an answer that was way larger than 0.006, 600 seconds later, that doesn't make any sense, and that's a good hint to you that you're going to need to go back and re-look at this question, okay? So let's move on to part D of this practice problem. At what time is the concentration equal to 0.0015? Explain how you know your answer is correct. So the question here is a little different than the other two that we've just answered, but it still mentions time. So we still have to work with the integrated rate law for first order. So again, we see this here. The only difference is now I've put in my natural log of this new concentration they've given me, and my time is my X value that I'm solving for. So I'll find my natural log of concentration that they've given me. I'll solve for X algebraically, and I get that X is equal to 606.5 seconds. So does this make sense? That a concentration of 0.0015 is going to take more time than 600 seconds? Well, the answer is yes, and here's why. At 600 seconds, our concentrated was 0.00157. So if we're going from 0.00157 to 0.00150, well, that's a very short change in concentration. So the difference in time there should also be very short. And it is. 6 seconds is pretty short, okay? So that's it for this practice problem, and that is all that we're going to do videos on for 5.3, okay? So let me know if you guys have any questions, and move on to the homework and the official practice problems below, okay?